Welcome to our exploration of search strategies in artificial intelligence, where we dive into how intelligent agents navigate through complex spaces to find solutions. In AI, search strategies are essential tools that enable agents to explore possible actions and outcomes, whether it is playing chess, navigating a maze, or solving a puzzle. Effective search strategies help the agents make informed decisions. When designing goal-based agents, we focus on environments that have the following characteristics. Fully observable, the agent has complete access to the environment state. Deterministic, outcome of each action is predictable and does not involve randomness. Discrete, the environment has a distinct, separate states and actions known. The agent has full knowledge of the environment and its rules. In such an environment, the solution to reaching a goal is a fixed sequence of action. The process of finding the sequence is known as search. Search involves exploring the possible action to determine the optimal sequence that leads to the desired goal. Once the agent starts executing the determined sequence of actions, it operates as an open loop system. This means that the agent can ignore its percepts and focus slowly and following the predetermined sequence, as the action will reliably lead to the goal state. Key concepts for goal-based agents includes number of components. Among these, the first one is the initial state. This is the starting point from which the agent begins its search for the goal. It defines the current configuration of the environment. Then following actions, these are the possible moves or operations that the agent can perform in its environment. Each action can change the state of the environment. Transition model. This model describes the effect of each action on the current state. It answers the question, what is the result of performing a given action in a given state? It helps predict the new state that will result from executing an action. Goal state. The goal state is the desired and the condition that the agent aims to achieve. It defines what success looks like for the agent. And finally, path cost. This is the total cost incurred to reach the goal state from the initial state. It is typically assumed to be the sum of non-negative step cost, where each step has an associated cost. The optimal solution is the sequence of actions that results in the lowest path cost while successfully reaching the goal state. This means the agent seeks the most efficient way to achieve its objective, minimizing expenses along the way. Here is a simplified explanation of the key concept related to an agent navigating from Arad to Bucharest, focusing on the initial state, actions, transition model, goal state, and the path cost. Navigating from Arad to Bucharest. The initial state, the agent starts in Arad. Actions. The available actions involves traveling from one city to another. For example, moving from Arad to the neighboring cities. Transition model. The model defines the outcome of each action. For instance, if the agent travels from city A to city B, for example, Arad to Sibiu, it will arrive in city B. Goal state. The goal state is to reach the Bucharest. Path cost. The path cost is calculated as the sum of the edge cost, which represents the travel costs or distance between cities along the route taken. In this, the optimal solution is the sequence of action. that is city to city travels that results in the lowest total path cost to reach Bucharest from Arad. State space consists of all possible states that can be reached from the initial state through any sequence of actions. It can be represented as a directed graph. A directed graph consists of nodes and edges. Nodes represent the various states. For example, different cities. Edges represent the actions that transition from one state to another. For example, travel routes between cities. The 8 puzzle is a classic sliding puzzle that consists of 3 cross 3 grid with 8 numbered tiles and 1 blank space. Here is a simplified breakdown of its components. Components of the 8 puzzle are states. The state represents different configuration of the tiles in the grid. The 8 puzzle has a total of 1,81,440 states, which means there are 1,81,440 unique ways to arrange the tiles and the blank space. The possible actions involve moving the blank space or empty tiles in 4 directions. Left, move the blank tile left into the adjacent cell. Right, move the blank tile right into the adjacent cell. Up, move the blank tile up into an adjacent tile. Down, move the blank tile down into an adjacent tile. The path cost is typically set to 1 per move. This means that each action taken incurs a cost of 1. The total cost of solution is simply the number of moves made to reach the goal state. The goal of the 8 puzzle is to arrange the tiles in a specific order, typically as follows: 1, 2, 3, 4, 5, 6, 7, 8. The aim is to find the sequence of action that moves the tiles from initial state to goal state, minimizing the path cost. A search strategy determines the order in which nodes are expanded in a search tree. The choice of strategy can significantly affect the efficiency and effectiveness of finding a solution. Such strategies are evaluated based on the following criteria: completeness. Does the strategy guarantee finding a solution if one exists? A complete strategy ensures that all possible paths are explored until a solution is found. Optimality. Does the strategy guarantee finding the least cost solution? An optimal strategies ensure that best path to the goal is identified. Time complexity. How many nodes are generated during the search? Lower time complexity means the strategy can find solution faster. Space complexity. What is the maximum number of nodes stored in memory at any point during the search? Lower space complexity means the strategy can run on systems with limited memory resources. Some of the complexity metrics are time and space complexity measured in terms of maximum branching factor of the search tree, that is the average number of the children per node, and depth of the least cost solution, how far down the tree the solution is. Choosing the right strategy involves balancing these dimensions based on the specific requirements of the problem being solved, ensuring that the strategy is both effective in finding a solution and efficient in terms of time and space. Thank you for watching.